My name is Chen. I am from RK20. Today our group are going to present the modern control system mini project video. Our mini project title is Helicopter Dynamics Control System. Our group got 2 members. First is Lokoseng and me, Chen. First of all, I will briefly explain about the background theory. The performance of a control system can be described in terms of time domain performance measures or the frequency domain performance measures. It is usually necessary to specify the maximum allowable steady-state error for several test signal inputs and disturbance inputs. Next, these performance specifications can be defined in terms of the desirable location of the poles and zero of the closed-loop system transfer function, TS. Besides that, we can describe the performance of a feedback control system in terms of frequency performance measures. Then, a system can be described in terms of the peak of the closed-loop frequency response, MP omega, the resonance frequency omega m, the bandwidth, and the phase margin of the system. Next, we can add a suitable compensation network if necessary in order to satisfy the system specifications. The design of the network represented by GS is developed in terms of the frequency response as portrayed on the polar plane, the board diagram. Cascade compensation networks. The compensation network function GCS is cascaded with the specified process GS. This is the example of cascade compensation networks. The compensation network function GCS is equal to K multiplied with S plus Z over S plus P. Phase lead compensation network. The general compensation network is GCS equal to S plus Z over S plus P. When P is greater than Z, the compensation network is called phase lead compensation network. In addition, for some books, the transfer function of phase lead network also written as GCS is equal to 1 plus alpha tau s over 1 plus tau s. We can get these two equations from this graph. First, phi max is equal to inverse sine alpha minus 1 over alpha plus 1. Second, omega m is equal to 1 over tau times square root alpha, and the unit is in radian per second. The maximum value of the phase lead occurs at frequency omega m, where omega m is the geometric mean of p equal to 1 over tau and z equal to 1 over alpha tau. By using trigonometry relationship, we can obtain phi max is equal to inverse sine alpha minus 1 over alpha plus 1. In designing phase lead network, by adding a phase lead network to our system, we can increase our phase margin by phi max if we choose omega m value similar with our gain crossover frequency. However, since there is an addition to the gain as well, we have to expect our gain crossover frequency increase a little bit. In order to overcome this problem, add a safety margin around 15 degrees to our required phase margin. This is the general guidelines in designing phase lead network. First, we need to find the system phase margin PM and gain crossover frequency GCF. Second, we need to find the phi max, which is the required addition for phase margin and add safety margin. Phi max is equal to phase margin required minus phase margin current and then plus 15 degrees. Third, we need to solve for alpha. Fourth, we need to use alpha value in omega m formula, where omega m is equal to gain crossover frequency, and solve for the tau. Last, we need to rewrite the lead network transfer function in this form. GCS is equal to 1 plus alpha tau s over 1 plus tau s.
My name is Low Boxing. Our title is Helicopter Dynamic Control System. A large helicopter used two tandem motor rotating in opposite directions. The controller adjusts the tilt angle of the main rotor and thus the forward motion. The helicopter dynamics are represented by GS, which is equal to 50 over S times 0.2 S plus 1. We will show that Rx is the input, Yx is the output, while controller is represented by GCS and helicopter dynamic is represented by GS. Part A, we have to draw a board plot of the helicopter dynamic and determine the gain and phase margin of the system. B, you are required to design a compensator, lead or lag, so that the phase margin would be greater than 48 degrees. For your design, you are allowed to use Scilab or MATLAB for your work. This is the part A solution. Before we want to plot the plot, we have to find out the K gain. So we assume that steady state error due to a ramp input is less than 5% of the velocity of ramp. And then we already know that GS is equal to 50 over S times 0.2 S plus 1. And Rs is equal to 1 over S squared, and ESS, which is represent the steady state error, is less than 0.05. First of all, we have to find out the transfer function first. The equation of the transfer function is equal to K multiplied by GS over 1 plus K multiplied by GS. So now we just substitute the GS inside or into this equation, so we will get the transfer functions, which is equal to 50k over s times 0.2 s plus 1 plus 50k. So now we have to find out the ESS, which is the steady state error, and this is equal to limit SES. So we know that ES is equal to input minus output, which is Rs minus Yx. So we also know that Yx is equal to Tx times Rs, which is transfer function times input. So we also need to substitute the Rs and Tx into this equation. So finally we will get this equation. From this equation, we know that s squared can be cancelled out. After cancel out, we will get 0.2s plus 1 over s times 0.2s plus 1 plus 50k. When the s is approaching to 0, we will get 1 over 50k. As we know that ESS should be less than 0.05. So we just substitute the 1 over 50k into ESS. So that means 1 over 50k is less than 0.05. After doing the calculations, we will get k is more than 0.4. So let's say we just choose k is equal to 1. Just now we say that k is equal to 1, means GS remains unchanged. GS now is equal to 50 over s times 0.2 s plus 1. So we just use this GS to plot the board plot. So where we want to plot the board plot, we just using the Scilab to plot it. After plotting, we will get GCF, which is gain crossover frequency, and also PM. PM is phase margin. In order to get phase margin, we must know GCF first. Where is the GCF? GCF is the point where the magnetic goes zero. So that's mean here. GCF now is found that is equal to 2.454 something. So at this point, we just draw a straight line ideal here, so we can get the phase margin, which is equal to 17.964 something.
In addition, gain margin cannot be determined because of there is no phase cross frequency.
5 steps to find GCS. First step, find the system phase margin and gain crossover frequency. From the Scilab graph, we can get PM is equal to 17.964 degree. Gain crossover frequency is equal to 2.454 hertz, but we know that GCS must be in radian per second unit. So we need to do a little conversion, as we know that 1 hertz is equal to 2 pi radian per second. So we're just using this to do the little conversions. Means that 2.454 hertz times 2 pi, we will get 50.419 radian per second. Step 2. We need to find out the Vmax, which is required addition for the phase margin and add the safety margin. The equation of the Vmax is equal to PM required minus PM current plus 50 degree. So the PM requirement is equal to 48 degree, and then the current PM is 17.964 degree. So these three values is add together, we will get 45.036 degree. So third step is solve for the alpha. We know that sin Vmax is equal to alpha minus 1 over alpha plus 1. So we just substitute the Vmax into these equations. We will get alpha is equal to 5.839. Come to this step, just use alpha value in omega n, formula where omega n equal to gain crossover frequency, and solve for the tau. So we know that omega m is equal to 1 over tau square root alpha. So we just substitute the omega n, which is equal to 15.419 equal to 1 over tau square root 5.839. So we just do a little calculation. We will get tau is equal to 0.0268. Fifth step. This step is just to rewrite the lead network transfer function in this form. We know that GCS is equal to 1 plus alpha tau s over 1 plus tau s. So we just substitute alpha and tau inside this equation. We will get 1 plus 5.839 times 0.268 s over 1 plus 0.0268 s. So finally we will get this equation, which is equal to 1 plus 0.156 s over 1 plus 0.0268 s. Actually, this coding is just used to determine the GCS equation whether correct or not. So we just insert our GCS equation and also GS equation into here and then execute it. We will get GCF and PM. And then we found that PM is equal to 48.159 something, which means that this value is already greater than 48 degree. Actually, this proves that GCS equation is correct.